Next, let's look at page 465, where we consider the growth rate. The growth rate just means how fast is the function increasing. For example, let's look at the difference between x squared and x cubed. As you can see, x cubed grows quite a bit faster than x squared. In fact, what we call it, the way your book call it, is that x cubed grows more rapidly. But that's not how I call it. I mean, in my day, we call it x cubed dominates x squared. Okay, the word dominates doesn't mean it grows 5 times faster or 10 times faster. It means it grows infinitely faster. So, and then let's look at the next example. Both things are x squared, but one of them is x squared, and the other one is 3x squared, the one at the bottom of the page. Now that one, as you can see, eventually one grows 3 times as fast as the other. However, we don't care about 3 times as fast. 3 times as fast is still just a number. We want one function dominates the other only if it grows infinitely fast eventually. Okay, in the beginning it might not do that at all, but eventually you know it's going to take off. Now let's look at, so with that, please do example 4.45 as your homework, because that's very straightforward of applying the L'Hopital's rule. And as a result of that example, you will notice that two things. Number one, the exponential function grows very quickly. For example, consider the exponential function with, say, what is that, x, or x squared. You know, so in the beginning, nothing looks very exciting, that necessarily, but very quickly, things get out of hand with the exponential function. And so the exponential function dominates x or x squared. And on the flip side, the logarithmic function is extremely slow. Look at how slow it is. It grows very, very slowly. Okay, set in such a way that even x is bigger than the logarithmic function eventually. This is at the bottom of the page. So exponential function grows extremely fast and dominates the x to the power what is that, x squared. On the other hand, the logarithmic function is basically being dominated by every last thing. Now, so eventually, if you can prove, well, we're not going to do it, but you can prove that these two basic facts. One, exponential function grows more rapidly than any x to the power p. Okay, for p, any p that's bigger than 0, the exponential function will eventually grow faster. It might take a while, but it will get faster even towards the end. And that is, more rapidly means dominate. It'll be infinitely faster. On the other hand, the logarithmic function is so slow that eventually x to some positive power, doesn't matter which power it is, will dominate the logarithmic function. Okay, even the square root of x, which grows slowly, will dominate the logarithmic function. Basically, everything, all x to the power p will dominate the exponential function. And again, dominate means it will eventually be infinitely faster, not just 5 times faster or even 1,000,000 times faster. If it's any kind of set number faster, it's considered the same rate. If it's 1,000,000 times faster, it's the same. It grows at the same rate because the ratio equals to a fixed number, which is 1,000,000 or 1,000,000,000. But in the dominate functions are the ones that grows infinitely faster eventually. Okay, there is no number that you can fix that is more. You get to be 1,000,000 times faster than it's 1,000,000,000 times, and so on. It just gets faster and faster. There's no end to it. So with that, we come to the end of this section. So the first thing I want to do is prove the L'Hopital's rule infinity case. But before that, let's look at the homework. The homework we should do for the L'Hopital's rule section is on page 470, problems 357, 59, 61, 63, 65, 69, 71, 73, 75, 77, 79, 81, 83, 85, 89, 91, 93, 95, 99, 401, 03, 05. So that's that. Now, and that I know that looks like a ton of problems. That's roughly double the number of problems you do, but most of them are fairly short and sweet. So you're basically doing maybe a half of problem or even a third of a normal problem. And it's good to do a lot of L'Hopital's problems because that way you get a solid hang of it. So having said that, let's first, so part of the homework is to prove L'Hopital's rule. So at this point, please stop the video and go do your homework. And when you come back, I will do the L'Hopital's rule next. Now the L'Hopital's rule, that is to prove the infinity over infinity case. Okay, the book didn't mention it. I probably doesn't think it's worth mentioning, but it's not particularly difficult. I will show you what I did first, so that you can study it yourself if you wish. Can you see it? Yeah, that looks pretty decent. Now that might looks like, wow, that's a whole page of stuff. Actually, not really. About half of it is setting up the problem, just describing what we know, and figure out what we are trying to do. In other words, what are we doing here, right? So that's half the proof. So to prove the L'Hopital's rule, you have first you assume the 0 over we already proved the 0 over 0 case, so we assume that. Okay, so then that is, we know that. So to prove something, first write down what we know. So first we write down that we have, here's what we know. Okay, we're given that such information, that is the limit as x approach a, f of x is 0. There are a bunch of zeros here, which makes it convenient. And the limit of x approach a, g of x is also 0. So we have, and then and also if this is the case, this is a 0 over 0 case, then then we have the limit of the ratio of the functions equals to the limit of the ratio of the derivative at the point we prescribed. Now that is already proven, so we'll use that as information. So what are we trying to prove? We're trying to prove is here's in a situation where limit of f of x is going to infinity, okay, where this is infinity, and same as g of x. And in this case, does this also work? Okay, we already we already know, so we're trying to prove the infinity case. And so if this is true, okay, then this is then the infinity case also applies. X approach a, the ratio of the two functions is the same as the ratio of their derivatives, and this is the infinity case of the L'Hopital's rule. So that's what we're trying to prove. Like I said, just setting up the problem alone takes quite a while. Okay, now to do that, we're going to beat this thing to look like that so that we can take advantage of this, what's given. So to beat it into looking like that, what we're going to do is let a of x equals to 1 over f of x. Then this condition applies. Being the f of x goes to 0, then a of x, so a of x, the limit of a of x is as x approach a will be equal to 0, right? Because f of x goes to infinity, so you flip it over, it goes to 0. And the same as limit b of x. But let me write that down. Oops. something fell off. We'll deal with that later. Now, similarly, let b of x equals to 1 over g of x. And then in that case, then therefore, then limit b of x is also equal to 0. X approach a. So far, we're still just setting up the problem. We haven't done a whole lot yet. But you can see that I'm trying to take advantage of the 0 over 0 case. Okay, so but how are we going to do that? So let's calculate a of x and b of x and see something good falls out of all this stuff. So to calculate the stuff, then let's look at it. Then so let's calculate limit of a of x over b of x. Okay, now by the L'Hopital's rule, 0 over 0 case, this equals to the derivative. All right, so we'll write that down. And then b of x, b prime of x, limit. All right, so then, and then we'll actually calculate it. Okay, it's 1 over f of x. We'll use the, I don't even remember what rule it is. Well, we're just going to do it, okay? I can't remember which derivative rule this is. So that equals the limit of what is, now a prime of a is 1 over f, so a prime would be minus f prime of x over, what? F of x squared. Okay, that is the chain rule, right? You take minus 1, and then f of x becomes squared, and take the derivative of the inside by the chain rule, and that is that. All right, so that should be good enough. And then similarly, the b of x, you take the derivative, it equals to the same thing, except with g of x. X approach a. So to take the derivative of b of x, it becomes gx squared on the bottom, and then g prime of x on top. X on top, and don't forget the negative sign. Okay, is mine. Let's see, where's g of x? Okay, minus 1. 1 over this is minus 1, and then squared, and then the derivative of the inside, chain rule, and yeah. Anyway, so there's that. So we have a big long fraction. And to do fraction, I should mention that when you have a fraction, to divide, this fraction is dividing by this fraction. That's the division line. The longest line is the division line. And when you divide by a fraction, you invert and multiply. So let's do that. So that equals the limit x approach a. The top thing, we'll just write it down. Okay, let's copy the stuff down. So there is a lot of writing here without much going on, really. Okay, and then we'll do the invert and multiply of the other thing. So equals to, so then g of x becomes on top and squared over negative g prime of x. All right. Okay, so now what? Now we are kind of not sure what to do. But however, we remember what is that again? That is the same as, what is a of x over b of x? A of x is actually, being by their definition, a of x is this thing, okay? And then b of x is that one. So a of x, b of x, will put the original functions in, which is f of x on the bottom, and g of x got flipped on top, because this is actually the limit of x approach a, g of x over f of x. Okay, so then you look across here, you notice, okay, so then you notice there's a g of x over f of x here, and there's another g of x, two of them, g of x over f of x here, so we can cancel them out because the limits are all nice and smooth, so you can go in and out at will. Okay, so then that equals to So there is a g of x over there and f of x over there. So we'll write there are two negative signs which will cancel out. We don't have to worry about them. So then we will write down on this side what's left is limit x approach a f prime of x, we'll keep that one, prime, x over g prime of x. Okay, and then what's left on this side? This side, we will cancel out one of them, okay? And then the other one, we'll move it to this side, which means we'll flip it over, and that becomes f of x over g of x. When you do the cancellation, get rid of one of them, and then flip the other one around because you're moving it to this side. And so then, and that is the answer. Look at that. The answer has neatly come out. Now that proof might look long with a lot of writing, but actually not much happened. We just, we set up this and then we took the derivative, did some algebra, a small amount of algebra fractions, and out pops the answer. See, that's because the real work is already done here. So here we're just beating it to make it work. You know, the only difference is it went to infinity instead of 0. So how do you handle that? Well, you just do flip it 1 over, then infinity becomes 0. See, and that's how we got it to come out. So it's a nice, neat little proof. That I hope you were able to do it yourself or learn how to do this kind of stuff. Now, in this calculus course, we're not going to be doing a lot of proofs, but it's still neat to learn how to do some of the proofs. So let me erase the board. Now, I want to go over problems 357, 363, and 373. And I will go over it by simply showing you how I did it. They're all very straightforward, but still somewhat interesting. So if you have any troubles, maybe you can look at my one-line note and help you decode how to do it. And that's all I'm going to say about that. And the next problem I want to talk about is problem 369. So let's 369 is a cute little problem that turns out that you don't need L'Hopital's rule to do it. The problem asks you to either use L'Hopital rule or use something that you already know. L'Hopital's rule might work, I don't know, but there is a quick way to do this. And so let's write down the problem. 369 says we're trying to find the limit of something like x plus 1. 1 plus x, 1 plus x to the power -2 minus 1 all over x. The limit as x approach 0. I need to remember to talk louder. As x approach 0. So how would you do that? We'll just use one. Now this thing, what is that? It reminds you of this particular formula that we've been staring at recently, right? Let me show you what I did, 369. Okay, so you can, anyway, so continue writing. So the limit as, we're going by this formula, okay? F of x minus f of a over x minus a equals to what? This is the formula for f prime, or definition of f prime of a, okay? And then we'll slap this thing on that, okay? Now to do that, we'll define f of x equal to that thing right there. 1 plus x to the power -2. And then f of a then, a is 0. Okay, x approaches 0, so a is 0. And then f of a equals to what? Well, 1 plus 0, etc. is 1. So this totally fits into this thing. Therefore, this limit equals to so f prime at a. Okay, that's all this limit is. So let's take the derivative of f of x, this thing, and calculate its value at a, which is 0. Calculate its value as 0. So let's take the equals to take the derivative, which is -2, okay, and then 1 plus x to the power -3, or just put it on the bottom is 3. And then take the derivative of the inside. That's just 1. So that's that. And then we'll evaluate it at x equal to 0. And that just gives you minus 2 over 1. Minus 2. And that's the quick and easy answer. We don't always need to use the L'Hopital's rule. It's just we only use it when we need it. And this thing looks identical to that. And so we just pull out the old hat, the old trick from the old hat, and use that instead. And it works out very nicely. Next, let's do problem 375. So 375 is the limit of x approach 0, limit as x approach 0 of sine x minus tangent x over x cubed. All right, that is okay. First, we identify to use the L'Hopital's rule. What kind of deal is that? That is sine of 0, 0, tangent 0, 0, and then x cubed 0, also 0. So this is the 0 over 0 case, which means we can use the L'Hopital's rule. And so to use the L'Hopital's rule, then we go ahead and take the derivative, which is all right. I don't think I'll finish writing this thing. You just I'll just show it to you and talk about it to save us some time. Now to do the L'Hopital's rule on this case, we will take the derivative once, okay, which land us in the 0 over 0 case again. So you take the derivative a second time, and this time things what happened this time? Maybe it'll end up in 0, 0 again. So we'll take the derivative a third time. And finally, it landed up in a good position where we come up with the right answer. So this is this is a math. Because the reason is because there's the x cubed. So each time you knock it down, it becomes x squared, but it's still 0. Then you knock it down, it's x, it's still 0. Right? So then eventually knock it down, it becomes the constant. And then you're good. So that's all I need to talk about in this problem. The next problem, 377, the same thing, right? So you have some equation with e in it. You take the derivative once, it's still 0 over 0. You take the derivative again. Now you are getting somewhere. The difference is again the similar situation. The bottom is x squared, so you have to do it 2 times. And because each time you only knock it down by 1 power, and that's not good enough. So 2 times, however, it is good enough. Now let's look at the next problem. Next, let's look at problem 383. Now 383 has a slight twist, which makes it slightly more interesting than the others. That is, we're looking at the limit as x approach infinity of x sine 1 over x. Now this one, if you try to beat it with the normal L'Hopital's rule, it kind of because the 1 over x, then you get into a big mess. So then there's a trick to this, and the trick is let y equals to 1 over x. That's the trick. Okay. Then as x goes to infinity, so if as x goes to infinity, y goes to 0. So then this limit is the same as limit of y approach 0 of sine of y over y. Now that we already know what this is. This equals to 1. Okay. You can also use the L'Hopital's rule to prove it very quickly that e equals to 1, but this is something that we have seen several times. In fact, we saw even in the previous video where I draw this graph. Okay, this is the sine around 0. Okay, it goes down, and this is y equal to x. This is just the y, right? In this case, they are the same at the origin. They approach the same at the origin. So this equals to 1. Or you can apply the L'Hopital rule quickly and figure out that e equals to 1. And therefore, the answer to this problem is 1. instead of getting stuck in a huge pile of fractions and things when you try to use the L'Hopital's rule, this is how you get around it. So that's that. Next, let's look at problem 385. Now, 385 is limit of x. Let's look at my notes. And I show you my notes, 385. Okay, now you have x, natural log of x to the power 4. Now, at example 4.441 on the other side of the line right here, on page 480, we did something like this. It's x ln of x, but there is no power of 4. Now, before you then dive into some kind of a big complicated L'Hopital's rule, remember, natural log of x to the power 4, you can take the 4 down, right? And once you take the 4 down, it's just a constant. Otherwise, it's identical to the example 4.41. So you can just copy that and get it to come out very quickly. So, and sometimes, everybody knows the natural log of some power, you can take the power down, but sometimes if you're stuck in the middle of the L'Hopital's rule, you might forget about that basic fact. Next, let's consider problem 393, which looks quite intimidating. Okay, we're supposed to figure out what is the limit as x approach 0 from the positive side, x to the power 1 over x. Okay, now as x goes to 0, 1 over x is infinity. That 0 is like 0 to the infinity. What is that? And then you look at it and you're all puzzled, right? However, if you think the first thing when you see this kind of situation where the variable is on top also as well as on the bottom is let's take the natural log. So then we'll take the natural log. That is, we let y equals to this fraction here. Okay, y equals x to the 1 over x. That way we remember with what we're dealing with. And then so then we take the log. The natural log of y equals to 1 over x natural log of x. Okay, now what happens when as x goes to infinity of this thing? X goes to 0. Okay, as x goes to 0, limit x go to 0 of this function. Now, as x goes to 0, I'll write down the limit here. That is limit of x approach 0 from the positive side, natural log of x over x. Okay, now think about it. As x goes to 0, natural log of x goes to negative infinity. Okay, minus infinity. This goes minus infinity. All right, and then this x just goes to 0. So you have a minus infinity over 0 situation. Well, what happens when you have infinity over 0? Well, what happens if this was 1, negative 1? Negative 1 over 0, it goes to negative infinity. So if it's negative infinity, it for sure goes to negative infinity. So this goes to minus infinity. And that is what natural log of y goes to. Okay, then where does y go? If the natural log dives down, that means the function itself is going to 0. So then y approaches 0, and that's our answer. Y is the original function. So and if the natural log dives down, right, the function itself means it will be it approaches 0. That's all. That's how remember the natural log graph. Okay, it dives down next to 0. So if the natural log goes to 0, function itself, natural log goes to negative infinity, function itself goes to 0. So that it would be our answer. Next, let me clean the board. So in the previous problem 393, let me show it to you here, and I already erased the board, where you notice that there's no need for L'Hopital's rule. You just pull in some trick and out pops the answer. The same as the previous question 389, which I forgot to mention. You have some kind of a fraction. Well, you just multiply out the fraction and then everything comes out nice. That's all. Okay, and so I won't mention that because we don't need the L'Hopital's rule, and then we'll move forward. Next, let's look at the problem 395, which is quite interesting actually. And if you look at the way the problem's set up, let me write it down first. We're supposed to find the limit as x approach infinity of 1 minus 1 over x to the power of x. Now, if you look at this thing, something like this happened in chapter 1 where the definition of the number e was given. Okay, it looks something like this. But we're not going to care. Okay, I'm just mentioning that as in passing. We're going to use whatever our tricks to calculate what this thing is. Because in chapter 1, when we did come up with something that looks like e, we didn't actually prove it. So, but now we're going to calculate this thing and see maybe with the help of L'Hopital's rule and see where it gets us. So then the trick is whenever you have something, a function to the power of some kind of x, then let's use this trick. Y equals to what's in there, the function itself. Okay, and then we'll take the natural log of y. So then the natural log equals to so then ln of ln of y equals to, okay, x natural log of this stuff, 1 plus 1 over x. And then we'll put it into an entire fraction, which is x natural log x, what? See? Did I suddenly turn it into a plus for no reason? I do that sometimes. Anyway, it's minus, okay? Minus, please. All right. So it's minus, and then so we get this thing, and we'll turn this into an entire fraction, I guess. That's what I did. I should show you what I did so that you can use it for reference. All right, that's enough showing, and let's keep talking about this. So then that equals to x. Okay, we will turn this into a fraction by dividing the x as 1 over x. So, okay, push the x on the bottom, and this is some fraction. We'll put it as this, x minus 1 over x, which is that. And then we'll look at this thing. What is this? What are we doing here? X goes to infinity. Okay, so the limit states we're considering what happens when x goes to infinity. Now, as x goes to infinity, then that is actually, I don't even think we need to do that. Why didn't I scratch that out? Oh, sorry. We don't need to do this. We'll just keep it like that, okay? So 1 minus 1 over x. So as x goes to infinity, then this becomes 1, okay? And natural log of 1 is 0. So that goes to 0. And then x goes to infinity, same thing. 1 over x goes to 0. So we have a 0 over 0 case. Now with that, then we can apply the L'Hopital's rule. Okay, the L'Hopital's rule, applying the rule that equals the limit as x goes to infinity. Now, remember what we're doing here. We're only doing the limit of natural log of y, not y itself. Later, we need to use the e to prop it back up, right? Because we took the limit, we slapped on the natural log, so we later need to do the e. But for now, we'll continue. So then, taking the derivative of this thing, we get the natural log of this is 1 over 1 minus 1 over x times the derivative of the inside is negative, and then another negative makes it positive, divided by x squared. Okay, 1. And then positive 1 over x squared all over, same thing here. So that it becomes minus 1 over x squared. That's the derivative of the bottom. Now we have a bunch of division lines. Do not let the division line confuse you. You just work on each part and get it to clean up. And in this case, that might not even be necessary. It's not, okay? Because we're just going to let x go to infinity while it's in this shape. Because being that x is going to infinity, that equals to what? X goes to infinity, 1 over x is 0, so this thing is just 1. X goes to infinity, this thing is 0, okay? X goes to infinity, wait a second. Let me see. Wait a second. No, sorry, I forgot something. This is the same stuff, so we are just going to cancel this out. Except for the negative sign, we might need to keep it. So we're just following this. This equal to 1. Okay, x goes to infinity, this is 0. So this whole thing equals to 1. Except for the negative sign, so we have minus 1. And then, so the natural log of y goes to minus 1. That means y goes to e to the power 1, okay, to reverse the natural log process that we slapped on before. And so we'll reverse it and get back minus 1, sorry. So this is equal to 1 over e, or e to the power minus 1. Yeah, that's good enough. And that is the right answer. As I mentioned in the beginning, this looks similar to the definition of e, but it isn't. It's actually the definition of 1 over e, but it's still close, okay? E itself is something that looks like this, except I think there's a fraction here. It's 1 over x or something. Well, whatever. We'll deal with that later. And yeah, and anyway, so the point is we have an answer, okay, of a problem that before this section it'd be nearly impossible to do. Like, how would you even calculate that? There's x here, x there, and a fraction, and but with this simple trick, the answer pops up quite readily, right? So that's problem 395, which is a neat little problem. Next, let's look at problem 399. Now, I went back to using the original definition of the derivative to solve this problem, but in reality, if you use L'Hopital's rule, that's even faster. Okay, you can basically do it in your head. So either way, pick whichever method you like. So let's look at the next one. The last problem I want to talk about is 403, where you're supposed to calculate the tangent of x to the power x. Now that might sound tough at first, until you realize the tangent doesn't mean anything. You can just take the tangent out. That is, you calculate what's inside x to the power x as limit x approach 0. And once you figured out what the inside approaches, then you slap the tangent on the answer. That's all. So x to the power x is a basic one problem where you use the natural log trick. Okay, you take the natural log, you apply the L'Hopital's rule, and you calculate something, and you put the e on it to make it go back. Okay, and when the natural log goes to 0, then the answer itself goes to 1, because e to the power 0 is 1. And then you don't forget to slap the tangent back on there, so the actual answer is tangent 1. And that's about it, right? Let's see, let me turn this thing so you can see it better. Okay, that looks better. So that marks the end of the section on L'Hopital's rule.